like I promised, I am going to give you an example of a hypothesis testing with the data set that I said we should download in the end of class on Tuesday. This is from the Federal Reserve of St. Louis. It's the Consumer Price Index of all urban consumers of all items in the U.S. city. Essentially, what this is calculating is from every 1 point, it's looking a year in the past to see the percentage change in inflation so that we can kind of look at this as a way, not necessarily as, because the value of the dollar changes over time. Here we can look at just the overall impacts to you, like the consumer going into the marketplace, like how much of a percentage impact does the price change have on you? Like, what does it look like to you from a year in the past? That kind of helps get rid of this whole issue with like time and the dollar getting more valuable and blah, 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 blah. So we can download this as a CSV or an Excel. If you download it as a CSV, you're just getting the raw data. That's how I typically download stuff because I'm just looking for data manipulation. But Excel is also another great form that will tell you exactly, give you like this README file that gives you like when you downloaded it and all of the information here, so that when you down the road, if you publish any of your work, you actually know exactly when you downloaded or accessed this information, which is kind of important in data analysis in general. Because as you can see with how we update numbers, when new numbers come in and it becomes more reflective, we correct for that. Okay, so where was I? We're here. Oh, we're going back over here. We can see various different times of increased inflation. Like in the 70s, we saw some stagflation, and they were pretty impactful. We can see some deflation over here after the 2008 crash. And what we're going to compare is that over the entire time that we observe this variable is the time period from 2020 that we observe this inflation increase. Is it statistically different than the entire data set that we're observing here? So we are going to develop not only just the hypothesis testing and the equation, we're going to design the test. So it's going to be a little bit more in depth than what you will observe in the midterm, because we're going to figure out what number we want to test. Okay, to do that, we have data from the last 77 years. So we are first going to figure out the overall average observed, or the descriptive statistics for an entire population. Now we could do this manually. We could calculate the mean, the mode, the median. We could get the standard deviation, and we could do that all manually within the formulas. But we can also just do that by going to data analysis, going to the descriptive statistics add-on, and then taking this bar and going through the entire data set, boom, taking this guy, getting up here, we're going to put this now in a new box, this new descriptive statistics. So we have now the entire data set from B2 to B933. We're going to put the descriptive statistics in D1, and we're going to make sure that these are checked, the summary statistics and the confidence interval. Okay, hitting OK. We get this new column of descriptive statistics for historical percentage change in CPI. So the mean is 3.52. So historically over time, from 1 year to the next, the average change in the price that consumers experiences is about 3%, right? Goods get about 3.52%, a little bit more expensive. And that's, of course, in the background, you're getting your like wage increases and all of those other things are occurring in itself. But the price itself of the good is getting about 3% higher. Okay. Our hypothesis testing is looking at whether the inflation of 2020 to now is historically different from the total population observed. That's kind of the question. I'm going to put in here at the 5% level, and you'll see why at the 5% level in a second, once we get to the p-values, because I'm going to give you that information in the midterm. It's going to be like 5, 1, 10, whatever. That's going to give us what we're looking for. Now we're going to write out the actual test. And you do that when you write the H null or the H alternative. And all that means in your slides is going to be HO or HA, right? So that's, you can go up to, is it over here? No. Yeah. Alternative hypothesis or the null hypothesis. And then you can observe that here as the HO or the HA. Okay. And we're looking at taking this, we're asking whether or not this subpopulation from 2020 to now, so a total of 2020, 2021, 23, 24, no, 20, 21, 22, 23, 24, and then so 5 years times 12 plus 8 months, 68 months. Is it statistically different than what we observe over our entire period of information? Okay, so that question is not whether or not our sample is bigger or larger than this number that we're calculating, or that, so either one. So it's not bigger or lower than that. We're looking at this two-tailed test, whether or not that value equals the other. So whether the inflation is historically different than what we observe over the entire time period. So in that case, we're talking about a CPI of 20, we'll just call it 20 right now, equals, or we'll go 20 to 2025, equals 3.52, or the CPI 2020 to 2025 does not equal. And I'm going to put the exclamation point equals as a way to write this out. If you notice in the R code, that's how R determines whether or not it's an equal or not equal sign. So this would be 3.52. But there's also other really cool ways that I haven't even gotten to show you guys yet, like inserting an equation. So if you go to, let's say, insert over here to the right side, equation, you can then write out a statistical equation in kind of mathematical form here. So let's go. Let's say CPI. If anyone's familiar with like LaTeX, you can use LaTeX code to kind of write out equations with indexes and everything. And here we're at the CPI 2020-25, and we can actually use this equal, doesn't equal sign and write 3.52. And so this is like a fancy way to do that same exact thing with the other code. Right? So we have equal, not equal. I mean, you could have written this out too. This is just the mathematical way of writing it out. Okay. So our test now is to look at the sample of 2020 to 2025 of August and whether or not it's statistically different than our historical average at the 5% level. From here, we can just do another descriptive statistic table by going to data analysts, getting the descriptive statistics, and now what we're going to do is just change this input range to the input range that we're interested at. And we're scrolling down to 2020. Okay, 2020, we got this, 866. So go over here, go to 866, B to 93. Now we have the range from 2020 to August of 2025, which will be 68 months. And we're going to need to put this in a new thing so we don't write over any of this information that we have down here. Okay. Summary statistics, confidence interval. Perfect. And here is our new descriptive statistics for 2020 to 2025. And what we have is a mean that's higher than what we observe here. So we have 4.02. So it could be that it's statistically different than everything we observed and the variance of all of it. We also have a standard error here, which is like 0.09, and this one's 0.2. And the main driving factor of that, of course, is the number of observations. When we look at the standard error, which was in the same file of statistical inference, so we go back up to, yeah, this guy. This is the, we can kind of like do it here. The standard error of the mean, right? That's the this is what the basic standard error operation is this idea of looking at the standard deviation of the total population. So we are estimating from this guy, the infinite population estimator. So it's taking that standard deviation here, taking the square root of the number of observation -1, 68 minus 1, which would be 67, and then calculating the standard error. So as that number goes up, as the count of observations go up, that number of standard error goes down. Okay. So for us, we want to do the t-statistic, which is, this idea of taking the actual sample mean that we observe, minusing what we're testing, all over the standard error. Or in this one, which is like the very helpful slide, is where we're taking the t-test of either the lower test, the upper test, or the equal test. And for us, right now we're currently taking the upper test. So this is the Excel code. Here, well, okay, but we need to actually do the t-test, sorry. I'm sorry, I got ahead of myself. This is the t-test. This will be the p-value. So our t-test statistics here is going to be, okay, equals our mean minus the observed mean all over the standard error of the sample that we took. That gives our t-test 1.72. That's kind of low. It's going to be really like squishy whether or not we get significance of our p-value. If you guys remember, the p-value, right? We talked about this in class with the 10% level being okay. The 5% level being pretty good. Oh gosh, why is this percentage coming up? The 1% level is statistically significant. And the 0.1% is very statistically significant. Okay. Oh, I just put it down to 0. Okay. I specifically called for the 5% level, right? Here's the question, 5% level. I'm just asking for a pretty good. What does the p-value correspond to? Well, it corresponds to the actual percentage of you making an error. Like basically the 5% says, I am willing to take a 5% risk of rejecting the claim when it's actually true, or accepting the claim when it's actually false, right? That was like kind of the meme here. Essentially, this corresponds to risk. 10%, you're saying like, I'm risky. I'm willing to I'm taking a gamble. 10% chance, it could be right, could be wrong. 10%, sure. 5% is like, we're getting down there. 1%, you're saying like, I am very risk averse. I want this to be accurate. And 0.1 is like, it's going to be accurate. It better be accurate. It better be a real true reflection of the population mean. In the question I give you, it's 5% level. So now that we've calculated our t-statistic, we've looked at our p-values, now we're going to like actually calculate the p-value from our t-statistics, which is in that slide, this yellow one. Here's, right? So p-value, this guy. So p-value, we will go t distribution, two-tailed test. That 2 and the t represents the two-tailed test. So t test distribution of two tails. This one's going to be the one tail. This is the two tail. This is actually the right tail. So that means, like, if you don't want to do that inverse, here, I'll show you. If you don't want to do the inverse, that right tail test is going to be like the RT is going to give you this upper tail test. Okay. We are taking t-test minus the degrees of freedom, which is 68 minus 1, because we always have to penalize the observations we have because we're not taking it from the true population. And our p-value is 0.08, which is above the 5% threshold that we have allotted ourselves, which means it's not even pretty good. It's okay. It's not a clear okay. Like, it's still in this, like, could be right, could be wrong realm. Like, it's just not really, like, we don't have as much confidence. But originally stated, I wanted 5%. So that means that from here, we cannot reject our null hypothesis, the first hypothesis, the fact that the CPI is equal to 3.52, which means that we don't have enough evidence to say that this mean is anywhere different than the historical overall average percentage change that we see in the CPI. And that kind of makes sense, right? Like, if you look at this inflation, yes, we saw some major inflation in the last 5 years, right? But also historically, we've seen way worse, up to 14% or 14.5% increase inflation, or 10. And here we only see 8. So historically, this is not that crazy of a variation over the entire time frame that we can't statistically say that this bit is statistically different or outside of the mean of our observations if it's normally distributed. And let's take a look. Let's see. What does it look like? Pretty normally distributed, right? You have some outliers, so it's a little bit skewed, but still it's fairly normal. Like, it comes up, then goes down, and it's probably hovered around the periods that we want. Yeah, like, it's hovered between this 1 to 2%, which is what, the Fed is looking for, is that 2% inflation rate. Okay. So from here, what you would say is then, okay, we got can't reject the null. It's above the 5%. We can't reject this guy. So we're going to say we cannot reject the null, and thus say that the time period between 2020 and 2025 is not statistically different than the historical change in CPI. Now, when you're doing your test, you can see this right here. So p-value this one says that the p-value is greater than the statistical significance, so you can't reject the null hypothesis, and the director does not have enough evidence to conclude that the store is more than 40 units. And in the same sense, we can't do that here, right? We can't say that our original hypothesis, testing whether or not it's different, is our information does not suggest that it is. Like, we can't say something statistically about the CPI change from the historical level. If it did equal it, if we had in here, instead of 5%, we said 10%, we could say that inflation is statistically different than the null at the 10% level for the last 68 months than the historical average. That's what you could say if you were to change that statistical significance level, which is kind of important when you're thinking about how willing are you able or willing to take the risk of making a type 1 or type 2 error in your analysis. I think that's basically it, and hopefully this was helpful.